Like a truss, the pin-connected frame is a rigid structure designed to support external forces. Frames have at least one member that is acted on by 3 or more forces. Trusses consist of only 2 force members connected at their endpoints. A machine also contains members that carry more than 2 forces and is designed to transmit forces from the input to the output of the device, often changing the magnitude and direction of these forces as well. Machines have at least one movable member, and unlike rigid pin-connected frames, are themselves non-rigid structures. Machines may vary in size and complexity, from small, precise robot arms to extremely large and durable mining trucks. The same methods are used to solve problems for both frames and machines. Consider the frame shown, which supports load W. The frame consists of 3 members joined together by frictionless pins. It is supported by a pin at A and a roller at D. A free body diagram of the entire frame is shown here. The external loads and reactions appear on the frame, and they consist of the weight W at F, AX and AY, the horizontal and vertical components of the pin reaction at A, and the reaction dx of the roller. Internal reactions holding the frame together are not shown on the free body diagram. To determine the forces that hold the frame together, separate the members of the frame and draw free body diagrams for each member. The forces at the hinges are now external and must be shown on the free body diagrams. Let's look at the free body diagrams for the 3 parts of the frame. In accordance with Newton's third law, the forces at C on member AD are in opposite directions from the forces on member CF. Similarly, the force at B on member AD is opposite the force on member BE. The force at E on member CF is opposite the force on member BE. Member BE is a short link, a special case of a 2-force member, and the force in the member acts along the member. If the 3 free body diagrams for the parts of the frame are combined, the forces at B, C, and E cancel, and we have a free body diagram for the entire frame. This method of disassembling frames and machines can also be used for problems that are otherwise statically indeterminate. The frame in this figure is identical to the previous figure, except that the roller at D has been replaced by a pin connection. Notice that there are now 4 unknown external forces acting on the assembled structure, but only 3 equations are available to describe the conditions for its equilibrium. Mathematically, this problem is not solvable because the requirement for complete solution is that the number of unknowns must be equal to the number of equations relating these unknowns. To obtain a solution, disassemble the frame and draw free body diagrams for each member. This process has increased the number of unknown forces to 8: AX, AY, B, CX, CY, DX, DY, and E. Each free body diagram has its own set of equilibrium equations equal to the number of unknowns, making the problem mathematically solvable. Disassembling a frame or machine into component parts increases the number of unknowns by exposing internal forces at each point of connection, and because each internal force appears on 2 free body diagrams, the total number of equilibrium equations available increases faster than the number of unknowns. For statically determinate problems, this will allow for a complete solution. In this example, the frame in the figure is supported by a pin at A and a link DE. Neglecting the weight of the members, determine the reaction at pin A and the tensile or compressive force in members DE, BD, and CD. As always, First, draw your free body diagram for the entire structure and then solve to find the missing reactions. Applying the equilibrium equations, we have the moment around A from which we will be able to find a value for E as 6.92 kilonewtons in tension, and then from the summation of forces of X and Y, we will be able to find the values for AX as 4.92 kilonewtons and AY as 3.46 kilonewtons. For member AC, member BD and CD are two force members. Therefore, the direction of these force members are known, and we draw a free body diagram of member AC. Components of C are shown in the diagram. So from the equilibrium equation, the summation of a moment about C is equal to 0. We are able to find a value for B of negative 6.92 kilonewtons in compression, and also a value for C of 9.79 kilonewtons in tension. In another example, a force is applied to the handle of the pliers shown in Figure A. Find the force applied to the bolt and the horizontal and vertical reactions at hinge A. As always, the first step is to draw a free body diagram. We know from the equilibrium equations we can take the moment about A, and we will have 160 newtons times the distance of 70 minus FB times 30 equals 0. We are able to find the value for FB as 373 newtons. We know that AX is equal to 0 because we do not have any force in the X direction. If we use the summation of Y forces is equal to 0, we will be able to find the value for AY as negative 533 newtons in compression.